I start?
Yes. Okay, we'll get started. So the next talk will be by Salwa Faour on distributed rounding.
Hello, everyone. My name is Salwa. I'm a PhD student, and this is a joint work with Mohsen, Christoph, Fabian, my supervisor, and Václav. So the title of this work is Local Distributed Rounding Generalized to MIS, Matching, Set Cover, and Beyond. So we give a general de-randomization method that efficiently solves a bunch of fundamental graph problems in the distributed setting. But before we get into details, let me just introduce the model we're working with. So given a network, we model it as a graph. Imagine a computer network where each node is a computer and the edges are communication links. We also assume that the graph has a nodes where each node has an order of log n bit unique identifier. And the goal is for these nodes to collaborate and somehow communicate with each other over the edges of the network in order to solve a graph problem, global graph problem on the network itself. So we want to devise a distributed algorithm where the computation proceeds in synchronous rounds. Each round, the computer can do arbitrarily internal computation. Each node can send a message to each of its neighbor and receive a message from each of its neighbor. And for the message sizes, we're working with the two classic models, the local model where we do not restrict the message size, but we limit ourselves to order of log and bit message size for the congest. However, in the stock, we ignore the message sizes, so everything today will work in the local model. The time complexity is simply the number of rounds. And at the end of the distributed algorithm, I would like every node to know its own part of the output. So if we're working with an independent set problem, I want to know whether it's in the independent set or not. So our general de-randomization method is based on a technique called local rounding, where roughly speaking, we start by finding a fractional solution to a certain fractional problem that we describe. And then we gradually round this fractional solution until we get an integral one to the original problem we want to solve. And we do this while essentially preserving the same fractional quality. Okay, so let me just talk a little bit about the previous work on local rounding. This method can be traced back and implicitly seen in the work of Hankovic, Karonsky, and Pankonesi, who gave the first polylogarithmic time deterministic distributed algorithm for maximal matching. Later on, this method has been explicitly used and successfully used for a bunch of graph problems, in particular, again for maximal matching. Fisher was able to achieve a better bound, order log squared delta log n for maximal matching here. And most recently, Ghaffari and Kuhn were able to solve delta plus 1 coloring in the same round complexity. And since we know 2 delta minus 1 edge coloring is just delta plus 1 coloring on the line graph, so in the local model, this also solves this problem in the same round complexity. Other problems where this technique has been used, hypergraph maximal matching, minimum dominating sets, and others. Okay, it's worth noting that there has been 4 classic problems over the 30 years or so that has been studied in the area of distributed computing. 3 of those you've just seen, and they other than MIS. So these can be solved in O log squared delta log n. Now we've just seen that. And by the way, this is the best current time complexity to solve them with a deterministic distributed algorithm. However, for MIS, short for maximal independent set, the best known result prior to this work was in O log to the power 5n by Ghaffari, Grunau, and Rozhoň. Okay, so one of the results of this paper is that we generalize this local rounding to give new or improved distributed deterministic algorithms that solve a range of graph problems, in particular MIS. So in this work, you'll see that this can be solved in order log to the power squared delta log n, nicely matching with the other 3 problems. And because we also know there's a simple reduction from O3 to MIS, efficient one, so you can see that this general rounding technique not just solves MIS, but all of the other 3. Okay, so our results is not just MIS. Well, we use this general framework to solve other problems, and including but not limited to giving a good delta approximation of the maximum node weighted independent set. Epsilon is a small constant. in order log squared delta W plus log star n rounds. W here is the maximum node weight. There's also an order log S approximation of the minimum set cover problem in this many rounds. S is the maximum cardinality set of the set problem instance. T is the maximum number of sets an element can be included in. So there are other applications to this method, including alternative way of coming up with the network decomposition, also in polylogarithmic rounds. And on the side, a much stronger result based on our rounding method was also presented a few days ago here at SODA. So there's other problems like minimum dominating set and maximum weighted matching and hypergraphs, but unfortunately I don't have time to go through all of this, and I won't. But what I would like to do now is illustrate and highlight the ideas of this de-randomization via local rounding method over at an example of a simpler problem. Okay, so what is the goal now? I give you a graph and I want to compute an independent set of size big omega n over delta. Okay, so we observe first that there's a simple randomized algorithm to do so. Every node initially marks itself independently with probability 1 over delta. And if we look at each edge where both of the endpoints are marked, then I want to also unmark the lower ID node. So I do this for every such edge. And at the end of the algorithm, I would output the set of all marked nodes, which now you can see is an independent set, hopefully. And what's the size of this independent set? Well, we notice that an expectation, well, first it's the number of marked nodes minus the unmarked nodes. And an expectation, it's this difference here. And to compute this, the expected number of marked nodes is n over delta. Take the sum over the nodes, probability of being marked. And the second term, the expected number of unmarked nodes, well, this can be upper bounded by n over 2 delta. To see this, just think of every edge where both of the endpoints are marked, right? For every such edge, we have to remove an unmarked node. So we can upper bound this term by the sum of over the edges, probability of an edge having both nodes marked, which will give us by simple calculation n over 2 delta, and thus achieving our goal of having independent set of such a size in expectation, which we really don't find so interesting. So we want a deterministic algorithm that achieves this goal. And to do so, we're going to de-randomize this algorithm via local rounding. So let's see a little bit how to do so. Step 1, we want to find a fractional solution. Remember? So let me describe this fractional problem that I'm talking about here. Okay, so I want to define a fractional version of this problem using this randomized algorithm that we talked about. And how am I going to do this? Well, by assigning fractional values for each node between 0 and 1. And the idea here is to interpret these fractional values as the probability of the node being marked when I plug it in my randomized algorithm. And then I can run my algorithm and get an independent set at the end. And the size of this independent set, so my fractional solution here will be the assignment of fractional values of the nodes. That's how I want to interpret it. And the fractional quality, well, it's a lower bound on the size of the independent set in expectation. This fractional quality, I'm calling it phi of x. The vector x is the assignment of fractional values. And it's equal to this expression here, which you can hopefully generalize from the previous algorithm. You go sum over the probability of being marked minus the other sum here. Okay. All right, so the next step, round this fractional solution to get an integral one while preserving that fractional quality. How to do so? Well, initially I want a fractional solution, and I describe this by assigning for every node a fractional value of 1 over delta. And the rounding is gonna proceed in phases. So in each phase, I'm gonna round up that value, double it, or round it down. So I do this in phases, and I require order of log delta phases. At the end, you see we get an integral value, right? And the idea here, I interpret the 1, if my fractional value is 1, then I'm marked, 0, then I'm unmarked. And the point here, okay, so I'm able to deterministically mark my nodes, right? And I get it also an independent set if I run that algorithm, which now is going to be deterministic, of size that fractional quality. which is simply the number of marked nodes minus unmarked nodes now. Okay, but the goal is to implement these surrounding phases now such that this quality, this phi, doesn't drop too much by at most 1 minus of 1 over log delta factor. Why does this help? Well, because notice that initially, if these are my fractional assignments, then I have an independent set already of big omega n over delta. And if this is how much the phi drops at each phase, then at the end, I will still achieve an independent set that is kind of preserved up to some constant, right? Which is still in big omega n over delta, which achieves my goal deterministically. So now let me just explain a little bit how we do this implementation. Okay, for convenience, I'm going to call this phi, the potential, the positive term, the utility, and the negative term cost. Okay? So to do this implementation, I rewrite my potential, which is utility minus cost, as the sum of the vertices utility per node minus sum over edges cost of an edge. And the idea is that every node, if you think about its fractional value, then what I wanted to do is to look at its utility minus the cost of its edges that are incident to it. And I wanted to round it up or down such that this doesn't decrease. Okay, so you can come up with a sequential algorithm if I go through the nodes, and this is what they do. But this is too slow for us. We want to speed it up, and we notice that if two nodes are not neighbors, they can be processed together. And if we do a coloring, okay, this works, but it's still a proper coloring and iterate through the colors, and that's how we do the rounding. It's still too slow. You can have too many colors. So how do we speed this up? Well, we use something called defective coloring. It's also a coloring of the nodes, but we allow some defects, so some monochromatic edges. And we want to do it with small colors and do the surroundings and show that this potential doesn't decrease too much. Okay, so let's see how we can do this. Before, let me explain the defective coloring. We want a generalized version of it, which is a weighted average defective coloring. I give you a graph. I set weights to the edges, non-negative weights, and some epsilon, which is a small constant. And okay, this is not a definition, but this is there's an algorithm that gives me such a defective coloring with that many number of colors, O of 1 over epsilon. So think of epsilon as 1 over log. So now I have log colors, log delta colors, such that at most an epsilon factor, so 1 over logarithmic factor of the total edge weight are on the monochromatic edge. And this algorithm is achieved in order 1 over epsilon rounds. There's some additional log star and factor there. So kind of log delta rounds if epsilon is 1 over log delta. Okay, recall my potential. Now, how am I going to use this defective coloring? The idea, okay, we're going through phases, if you remember, in the rounding. So in one phase, what I'm going to do is compute this defective coloring, and the weights of the edges are going to be the cost of an edge. And this epsilon, as I said, I'm going to choose it 1 over log delta. And then we're going to do this rounding scheme that we talked about, but on the subgraph induced by the bichromatic part. So we have this picture, sorry, I should have illustrated. We have a defective coloring. If you notice, there are some monochromatic edges. That's step 1. And then we round on the bichromatic part. Okay, so the idea is, now what happens to the phi if I do this in one phase? So recall the phi is the utility minus cost, but I can also rewrite it as the utility minus the cost on the bichromatic part minus that on the monochromatic part. And the monochromatic part is at most an epsilon factor of the total cost, because this is how I define my weights. They are the costs. Okay. So I know that on the bichromatic part, everything's preserved. I did the rounding there, proper coloring, things are good. But on the monochromatic part, what happens? Well, this can grow by at most a factor 4, just because remember the cost, it's xu times xv, so the fractional values of the endpoints of the nodes, which when rounded up can both be doubled at most. So this can grow by at most factor 4. Okay, so what does this mean? It means that now I have a set of new fractional assignments, okay, where the new potential is going to be the same as the old potential because this whole thing here is preserved and the cost over the bichromatic is at most that of the whole edge set, minus 4 times the cost on the monochromatic part, which I also know is at most absolute fraction of the cost, total cost. So the new potential is preserved, but it decreases that much in that phase. Now, the idea is that if I don't want it to decrease too much, then I would like to show that this cost, the total cost, is in big O of the potential. So if I show this, then I know my new potential is at least 1 minus some epsilon of the old potential, right? And this would be good enough for me if I run log delta phases, because at the end, I will have my potential doesn't decrease too much, okay, as I explained before. Unfortunately, I don't have much time. Okay, sorry. Now, initially, this is true. The cost is in order of 5x. You can see this by yourself if you think about the fractional assignments, they were 1 over delta. But this is not necessarily true, and after some few rounding steps, and that was a problem. We resolved this using different machinery, which I don't have much time to explain, but things work out. So now the final algorithm would be, okay, run those log delta phases and iterate through them, sorry. And then each phase, we run this defective coloring and then do the rounding on the bichromatic part. Okay, so the time complexity is step 1, it takes, okay, I forgot the additional log star factor first, but this is how much it takes, let's say roughly log delta. And the step 2, we have these colors, remember with the defective, so we're doing order log delta colors. So it's also order of log delta. So steps 1 and 2 log delta, and the whole thing will work in log squared delta plus log star and rounds. Okay? And now we can deterministically compute this independent set in that many rounds. I wanted to explain a little bit about maximal independence set, but I don't think we have time for this. But yeah, we're able to, in this paper, this was, we know of a randomized algorithm that solves this problem, and it's going to be de-randomized using this local rounding method. So we're going to have some fractional solution where we define a fractional quality and that we'd like to preserve while rounding that fractional solution. Okay, so not much time. Okay. At the end, well, yeah, this is the general method, and I think an open question would be where else can we use it? What other problems can we apply it to? Thank you.
Questions for Salwa?
So one question about the potential analysis over there. So you mentioned that the slide analysis doesn't work because the cost could exceed the potential value, right? But I'm just confused that because the potential is always going to be positive. So how come the cost could exceed the value of the potential?
I mean, the cost is always the cost of an edge is being doubled, right? So the cost can arbitrarily increase. But the potential, if you recall, whenever you're computing the new potential, it's the old potential. And what's happening? Subtracting, right?
I see.
So
yeah, I
it can go
yeah.
overboard and it's useless. Yeah,
I see. Thank you so much.
You're welcome.
Any other questions?
Is the defective coloring is done once or it's done from scratch every phase?
From scratch every phase.
And this is important?
I don't see how to get around. Yes, it is important.
Any other questions? Okay, then let's thank Salwa and all the speakers in the session again.